Hello, so in this video, we're going to be looking at something called the conservation of energy and also the work energy principle. Okay, so in the last two parts of the chapter, the last two videos, we looked at firstly work done. So, work being essentially the energy we put onto an object to move it, right? So, for example, pushing a box forward. Um, the energy we put onto the box in order for the box to move forward, right? And so then we saw that work formula is the force times distance, right? Um, and to remind you, work is in joules or nanometers. Not nanometers, Newton meters. There we are. Those are the units. In particular, you notice the joules because work is a form of energy. Because once again, it's the energy we put onto the object to move it forward. Okay. And we also looked at kinetic energy and gravitational potential energy. So kinetic energy being, well, the energy. So when an object gains speed, so get moves quicker, then it gets kinetic energy, and then gravitational potential energy is to do with as we get higher vertically, higher above the ground. So perhaps climbing up a wall, we're higher above ground, so you have more gravitational potential energy. Okay, because we're against gravity there. Okay, so that's what we looked at really. Okay, so firstly, then we're going to look at conservation of energy, and this kind of does what it says on the tin, really, and it's quite similar to conservation of momentum. So the idea is when an object moves forward, it's traveling, right? That if we don't add on any forces on the object throughout its journey. So if it goes from one point to another, if we keep forces acting on it consistent, right, then the energy must remain the same at the points in the journey. The object can't suddenly gain or lose energy by itself. Okay, only forces can change the energy, but if there's no forces acting on it, then energy remains the same at one point and another on its journey. So what I'm going to say is if no forces, and I'm going to leave this blank, and now I'm going to add on to that in a minute. If no forces act on an object moving, I'm just going to leave it act on an object, then the energy of the object remains the same. Okay? So for example, let's say a car has like, I don't know, 5,000 joules, right? It will always have an energy of 5,000 joules as long as no forces then act on the car. Okay, so the energy will always remain the same. Okay, so okay, so that's the idea essentially that the energy must remain the same unless we add on forces to the object. So no forces acting on the object keeps the energy the same. And so as a formula then, as a sort of mathematical formula, we could say that the gain in energy is equal to the loss in energy. Okay. And so what this is saying is that if we gain some energy, then to conserve the energy, we need to lose that energy as well. So if we gain some energy, then we lose the same amount of energy to keep it balanced, okay? To conserve the energy. And so what that means, I guess, more particularly, we've looked at kinetic energy and gravitational energy. So if we, let's say, gain some kinetic energy, then we have to lose that energy in gravitational energy, okay? So they kind of counteract. We're going to look into that with some examples in a moment to demonstrate that. We could also say, if we want to be a bit more precise, I guess, we could say that the change in kinetic energy add the change in gravitational energy, GPE, has to equal to 0, because then what this is saying is these two changes in energies, which gives me my total change in energy. Well, there is, as we discussed, energy cannot change if it's conserved. So the total change indeed equals 0. Okay. So those two different formulas, two different ways of looking at it, which are the same though. Okay, so that's the idea. Okay. Now, lastly, I'm going to fill this in. So I left it blank for a reason. And so what I'm saying is there's no forces acting on an object, so the energy has to remain the same, apart from gravity. Okay. Or gravitational forces. Okay. And the reason for that is that we already account for gravity in GPE. Okay, so we kind of account for that anyway, and it makes our life a lot easier because gravity affects everything, right? Weight or the gravity is always is always a force acting on any object. So if we already account for that, then that makes life easier. But apart from that, any forces like friction or anything like that, which affects movement, if there are no forces acting on it, then the energy remains the same at all times. Okay. Right. So we're going to look at some examples to demonstrate this. Okay. So here we're told a stone of mass 0.5 kilograms dropped from the top of the tower and falls vertically to the ground, hits the ground with a speed of 12 meters per second. Find the kinetic energy gained. Okay, so if I just draw roughly what's going on, we have a stone, and then we're told it falls down from a tower, right? So it falls down like this. Then it hits a ground. It hits the ground. And so it hits the ground, let's say here. And so we've got these two different points of the journey. We're at the top of the tower here, and then we're at the ground here. Okay. Now, we're also told it hits the ground with speed 12. So I mark that here, 12 meters per second. That's the speed on the ground. But also, quite subtly, we also know the initial speed at the top, because it'll be 0, right? It starts with no speed because it's been dropped from the tower. So it can't have any speed to start off with, okay? And so there we are. So then it wants, firstly, it wants the kinetic energy gained, okay? So that's hinting about changing the kinetic energy, okay? And we looked at this last time, and we know the change is the final kinetic energy, take away the initial, okay? That gives me my change from start to finish, okay? So we know the final speed is 12, so if we work out that kinetic energy, it's going to be half mv squared, or half times the mass, which is 0.5, times the speed of 12, all squared. Then the initial speed is 0, okay, so then it'll be half of 0.5, lots of 0 squared, and that goes to 0, so that means my change in kinetic energy is going to be 36, and that being joules, right? So there we are, okay. And I make a note that specifically the change is a gain, right? Kinetic energy is gained because very simply we are increasing the speed. It goes from 0 to 12. So I make a note this is a gain, okay. Then in part B, it's asking then for the potential energy now, which is gravitational potential energy loss. Okay, so we know that GPE is mgh. Well, we know the mass is 0.5. We know that G we take to be 9.8, just a number. Then H, now H, the height, that's the vertical height. Well, this is the height it falls, right? That's what we want. But we don't have that. We don't have how far down it fell. They don't have the height fell. So what can we do? Well, actually then, this is where conservation of energy comes into play, because if we look at this, what we've just discussed here, we know that the gain in energy is the loss in energy. Okay, so what that means is, if I just note that here, gain in energy equals loss in energy. Well, we know we have gained, as we discussed, the stone gains kinetic energy. However, the gravitational energy is lost, and it says it in the question, it's lost. That is because, again, simply it's gone down. Okay, it's going towards the ground. Its height is lowering. Okay, so that means it's a loss. Okay, so that means the gain in kinetic energy has to then match the loss in gravitational energy. And that's simply what we're going to do. So therefore, we can say that the loss in gravitational energy, GPE, matches the kinetic energy, which is 36. Okay? And that's it very simply. That's the idea of conservation of the energy there. Then in part C, and that being joules if you wish to add that on. Then in part C, then it's asking for the height of the tower. Okay, so we're not meant to know the height yet, but now we need to work it out. Well, then I'll just go back to what I discussed, that the loss in GPE, the gravitational energy, well, again, it has to be mgh, right? Which we discussed is 0.5 times 9.8 times the height h. Okay, because that's height travelled, right? That's the height. So that's how much energy, gravitational energy there is. Okay. So if you work out 0.5 times 9.8, that will go to 4.9 lots of h. But we know from part B that the loss in gravitational energy is 36. So if we then divide by 4.9, we get h to be 7.35 to 2 decimal places. And there we are. Cool, so hopefully that makes sense. That's the idea. So in this case, we gain kinetic energy as the speed increases. So that has to match the loss in gravitational energy as the object goes down. Okay. Right, let's have a look at this example. So now we're told a particle of mass 0.4 kilograms falls a vertical distance of 7 meters from rest. Calculate the potential energy loss. Okay. So again, we've got this situation where we've got some object that's falling down, and we're told it falls 7 meters. Okay. Now, I'm told, I'm told the mass. I'll use that in a moment, but I'm told it starts from rest. Now, rest again. Remember that means it has no speed. So if it starts at rest, means it has no speed initially. Okay? It starts with 0 speed. I don't know the speed after. Okay, I'll call that V. Okay, I'll call the final speed V. Right. So that's what's going on. Hopefully we can hear. So it wants me to work out the potential energy loss. So again, potential energy is gravitational energy, right? So the change in GPE in this case, well, again, that's going to be mgh. We know the mass is 0.4, g is 9.8, and h, we do know the height. It's gone down by 7, so times by 7. And then if we work that out, we get 27.44 joules. And there we are. Okay. And there we are. So that's the potential energy, and it's lost. Okay, it's lost because it's going down again, right? So it's going downwards, so it's a loss. And so what we'd expect then is that if we're losing this gravitational energy, we expect to make that up with gaining kinetic energy. So then what that means is because we lose GPE, so we lost in GPE, or should I say GPE lost. Actually, no, I'll just say loss in GPE. has to then be the gain in kinetic energy. Okay, these are the only two energies we consider in this chapter. It's, kinetic energy and gravitational energy. Nothing else for now. Okay. Well, we know that the loss the loss is again 27.44. We've worked that out. That has to then be the gain in kinetic energy. Okay. So, and so therefore it wants me to work out the final speed, but I'll call the final speed V. I've just called it V. It's unknown. I want to work that out. Okay, so then I know what the gain in K in kinetic energy is. I can also work that out with these two speeds, right? I also know that the change in kinetic energy is going to be the final kinetic energy. Take away the initial. And so the final speed again is V, so it's going to be half mv squared. Well, the mass is 0.4, so 0.4 lots of V squared. Take away the initial kinetic energy, well, that's zero, because it starts at zero speed. So simply, it's going to be half times 0.4 is 0.2 lots of V squared. And there we are. Okay, but we know that the change or the gain in kinetic energy is 27.44, so that means 0.2 V squared has to match that, right? They're both the same thing. Okay. Right, so then very simply then, I could just solve this for V. So if I divide by 0.2, I get 137.2. So therefore, if I square root that, I get 11.7 meters per second to one decimal place. And there we are, ignoring the minus from square rooting. Yeah. So there we are. Okay, so now we're going to look at the what we call the work energy principle. Okay, so before we look at this, I want to set the scene. So as an example, let's say I have a car, right? A very simple diagram of a car, right? And the car's moving forwards. Okay. Now, there's going to be, in this case, there's going to be a driving force that moves the car forwards, right? As we've seen before. And then there's going to be friction on the road. That's going to try to oppose it, right? So that's how friction works. If you move forwards, friction will act backwards to oppose it, right? And so there we are. And so we can actually label these as a forward force. Well, the force acting forwards, right? And then a backward force that, well, goes the other way, goes backwards, right? So hopefully with me here. Just a simple example. And so why do I bring this up? We're going to be looking at work again. That we looked at previously. So I'm gonna look at because we've got these two types of forces. We've got a forward force and a backwards force. Both of these forces are going to do work. So they're going to transfer energy onto the car. Okay, the forwards force is going to put energy onto the car to move it forwards. And then the friction or the backward force is going to put energy on the car to slow it down. Okay, so we've got this almost sort of like tug of war situation. One force trying to move it forward, one's trying to move it back. Okay, now the car's obviously moving forwards, so we got these. So we got sort of like, as I said, like one force trying to move it forward, one's trying to move it backwards. Now again, they're both going to do work, right? to move it forwards and backwards. So then we can sort of work out an overall work, okay, which is the difference of these two. So it's going to be the work forwards take away the work backwards, okay. Hopefully that makes sense. So again, when we got this situation of sort of two forces, well, two forces acting forwards and backwards, as I just done here. If we take away the forward, if we take away the work done from the forward force from the work done from the backward force, then we get the overall work at the end. Okay, that makes any sense. Okay, and ultimately, as you can see, the car moves forward. That's because the work done from the driving force moving it forward has to be bigger than in order to overcome the work from the friction to slow it down. Hopefully that made sense, okay? And hopefully you're with me with this. Now, why do I mention this? Well, this plays into this work energy principle, okay? So, when you can notice here as well, obviously I've now added forces on, okay? And if you recall, when we looked at conservation of energy, here, right, this section here, conservation of energy, no forces must act on an object in order for this to apply. What we've got now are forces acting on the object. We've got a driving force and a friction force. So now the situation's changed. So now there are forces on the object. So now that means energy is not conserved, okay? And so more specifically then, if we then work out then the change in kinetic energy and the change in gravitational energy, right? Again, if we work out the two changes in the total change of energy, what that turns out is now if we include forces, it equals the overall work done from all the forces. So it actually turns out it equals the overall work. Okay. Right, and so this is the work energy principle, because again it links energy, as you can see here, changes in the energies has to equal the work. Okay, right, and so these two formulas here we're going to use to look at some problems. Okay, before we look at some, I guess, proper examples to really demonstrate the work energy principle, because I think, especially for the first time, it can be a bit confusing. I know it was a bit confusing for me. I just want to look at a really broken down example to just really flesh it out. So what I've drawn here is again a situation. I've got something that's moving forward. So initially its speed is 2, then finally speed is 4. Okay. In addition, obviously the mass is 5 here. There's also a driving force, which is the force forward, okay? And then there's a sort of friction force that is backward. Also, the distance travelled is 10 meters, and I want to find the driving force D. That's the situation here, and we're going to use the work energy principle here, okay? Okay, so if I literally just state the work energy principle, that's going to be the change in kinetic energy, the change in KE plus the change in GPE equals the overall work. Okay, this is what I stated just recently, right? This is the work energy principle. This little formula here. Okay. Okay, so what exactly does this mean? Well, firstly, I'm going to look at overall work. Okay, I think it's probably the more confusing aspect out of everything here. So overall work, okay, and also as I've also stated, the overall work is the work done the work done forwards. Sorry, take away the work done backwards. Okay. So what that means is the overall work done is the work is sort of like a tug of war. So it's sort of it's the difference between the work done by the forward force, take away the work done from the backwards force. Okay, so what in this particular case, we're going to be looking at the work done by the driving force D, take away the work done by the force 12 here. So if I break this down, then if I now work out these two individually, the work done forward, so the work forwards first of all. Okay, well that's going to if I refer then back to the work formula, so remember work is simply force times distance. Okay. We looked at this at the start, okay? Work is force times distance. So the work forwards, I mean the work of the forwards force, which is D here. And so if I use this formula, that's going to be D, which is the force times the distance, which I said is 10. So very simply, the work forwards is D times 10, okay? Then work backwards, that's now going to be looking at the backwards force, okay? But now the backwards force, which again is opposite to where it's moving. So if it's moving forward, this is the backwards direction. We're going to do the same thing, but now with the backward force instead. So we know the force is now 12. So if I now look at the work formula, that's going to be 12 for the force, and the distance is also 10. Okay, so that's going to be 120, right? So if I do it here, that's 12 times 10, which is 120. Hopefully we've been there. That's the whole gist of calculating this overall work. So the work forwards, take away the work backwards. So the forward force and the backward force. Hopefully that made sense. Okay. So therefore the overall work, again, if I look at this formula here, simply the forwards work, so that can be D times 10 or 10D, take away 120. Okay, we're going to leave it as that because we need to find D. Right. Okay. Now we're going to look back to this main formula, which again, the work energy principle. Now we're going to look at the change in kinetic energy and the gravitational energy, which hopefully you are more comfortable with. Okay. So again, hopefully that made sense about the work there. Okay. So just simply look at the forward force and the backward force, calculate the work of them here. Okay. So now we're going to look at the change in kinetic energy. So that's then going to be the final kinetic energy, if we recall, take away the initial kinetic energy. Right, so firstly, the final kinetic energy, well, the speed is 4 at the final speed, so it's going to be half mv squared. So it's going to be half times the mass, which is 5, times 4 all squared. Then I'm going to take away from the initial kinetic energy, that's going to be speed 2. So the initial speed is 2, so that's going to be half of 5 times 2 squared. Then if we just simply work that out, I get 30. Okay, so there we are. And again, it's going to be positive because we're increasing our speed, so it's a gain in energy. Okay, then the change in gravitational energy, GPE. Well, actually, that's going to be mgh. But actually, there is no height change, right? But we're on a flat surface, so there is no work done. So it's going to be mgh. Well, mass is 5 times 9.8 per g, but there's no height, so it just all goes to 0. Okay? So actually now we have all the ingredients. If we sub it into the work energy principle, we can sub everything we know. So firstly, the changing kinetic energy is 30. So 30. So then we add on the GPE, which is 0. There's no change there, as we worked out. So the change in kinetic energy, change in GPE has to equal the overall work, okay, which we just went over. It's this expression here. We ended up with this 10D minus 120. Okay, so very simply then, at this point, we're just solving for D. Okay, so simply 10D, if we add 120, we get 150. Therefore, D 250 divided by 10. So D is 15 newtons. That is my driving force here, or my forwards force. Okay, so hopefully you are. That's the use of it there. There we are, and that's how we can use it. Yes, I hope that made sense. I've got this question here first. So here we're told a van of mass 2,000 kilograms starts from rest. After travelling 400 meters, the speed is 12. Constant resistance of 500 newtons acts on the van. Calculate the driving force. Okay, so before we do anything, let's firstly draw the situation. So I've got a van that's probably on the road, right? The van has mass 2,000. Okay, now I'm told it starts from rest, so it starts with 0 speed, let's say over here, and then it reaches a speed of 12. Okay, so that's my speeds. Then as for the forces, well, I'm told there's going to be a driving force, so that's going to act forward, right? That's where my driving force is. And then there's going to be a resistance force which acts the other way. And so that's going to be 500 newtons, right? So hopefully happy with that, right? So it's kind of like friction, right? But that's my force there. Hopefully happy with that. So I'm going to have to use the work energy principle here because effectively there are forces involved. So that's going to be work involved, right? Because forces have work. So remember the energy principle, the work energy principle says that the change in kinetic energy add the change in gravitational energy, GPE, has to equal the overall work. Okay, so if I work all these out bit by bit, so firstly the change in kinetic energy, well, remember that's always going to be the kinetic energy after, take away the kinetic energy before. So in this case, kinetic energy after, well, the speed is 12, so it's going to be half times the mass, which is 2,000. Times by 12 there. Then I'm going to take away by the initial kinetic energy, but initially there's no speed, so there we are. So we work all that out, that's going to be 144,000 joules there. Okay, then the change in gravitational energy, well, remember that's mgh, so that's going to be 2,000 for the mass times 9.8 for g. But hang on, what's the height? Well, there's no vertical height because it's not gone up or down, right? That will be my vertical height, but because it's on some sort of flat horizontal road, it's not going up or down, so overall there's no height, so it just goes to 0, right? And then lastly, the overall work, well, I said that's the work forwards, take away the work backwards. So what does that mean here? Okay, well, I'm talking about the forwards and the backwards force. So obviously the van is moving forwards, so this is my forwards force D, and I'm told the distance is 400. Okay, so the work of the forwards force is going to be D times 400, because remember work is force times distance. So it's going to be D times 400 for that, for the work forwards. Okay, then the work backwards, very similarly, right? This is my backwards force, so the work done is going to be 500 times the distance of 400. Okay, so 500 times 400 there, so hopefully happy with that. And so this simplifies to 400D, take away 200,000. Okay, and there we are. So now hopefully happy with that, so therefore I can substitute it into my work energy principle formula here. So the change in kinetic energy is 144,000 plus 0 for the change in gravitational energy is going to be the overall work of 400D take away 200,000. Then you can see I can work out D quite nicely if I just solve this equation. So I'm going to get D to be 344,000. Then I divide by 400 to get my driving force D to be 860 newtons. So we've got this question then. So here we're told a particle of mass 0.4 kilograms moves in a straight line across a rough horizontal surface. The speed of the particle decreases from 8 to 4 meters per second as it travels 7 meters. Then it wants me to work out the kinetic energy lost. Okay, so again, if I sort of draw the situation while we're on some sort of surface, uh, and if I draw a box to represent the object, the mass is 0.4. Okay, and we know the speeds, so we know initially it's 8. So I'll add that on here. And then it drops to 4. Okay, so at the end here, the speed is now 4, right? But we also know there's going to be a friction force. Well, it mentions friction. Okay, so I'll call that F, friction. We also know there's going to be friction because this keyword here, if you see a rough surface in a question, pay attention to rough in particular, that means it has friction. Okay, so I know because of that word rough, there's going to be friction involved. Okay, there's no mention of any sort of driving force. It's not necessarily a car or anything like that. There doesn't have to be a force moving forward. Not necessarily. That's really the only forces acting forwards and backwards. There. Okay, those are the only forces we really care about. Just the friction force. Hopefully, with me there. Then. Okay. Then it wants me then to work out the kinetic energy lost. So if we work out the change in kinetic energy. Well, that's going to be the final kinetic energy. Well, that's when the speed is 4. So half times the mass was 0.4 times 4 squared. Then I'm going to take that away from the initial. So it's going to be half lots of 0.4 times 8. Okay, we'll work that out. That's going to be minus 9.6. Okay. So it's a negative. So hopefully that you're aware that would mean it's going to be a loss in energy. Okay, and it says it in the question loss. We also know it's a loss because very simply the speed is going down from 8 to 4. So that means therefore the loss in kinetic energy, loss in Ke, is just simply the positive. It's just 9.6 joules, and there we are. Right, then in part B. Then it's asking to write down the work done against friction. Okay. Okay. So obviously we've got our friction here. Okay, so we know standard formula for work. So work by the friction force, so work by friction. It's going to be the friction force itself, so F, times the distance moved. We're told the distance is 7 meters. It travels 7 meters. So F times 7. Well, we can't work out at the moment the work because we need to work out what F is. But this is where we can use the work energy principle. Okay, so if we look at this formula, that we know that the change in kinetic energy and the change in GPE has to equal the overall work. Okay, and I'll say that's the work energy, right? That's the work energy principle used there. Okay, so we know that the change in kinetic energy, you have to pay, yeah, very important. You include any minuses here. So the change is a negative change, right? Because we're losing the kinetic energy. So we use minus 9.6. Okay. there is no change in gravitational energy because it's always on the ground, right? There's no height change. So 0 for that. And so then the overall work, okay? So that's telling me that the overall work, if I get rid of this now, the overall work is minus 9.6, okay? Again, that would be in joules. Again, it's going to be negative. You'll see why in a moment. So this is the overall work done. Now, remember, the overall work done can also be split up to the forward and the backwards force. Okay, so the work forwards and the work done in the backwards. Okay. So if I substitute that in, that's going to be the work forwards. Take away the work backwards is equal to minus 9.6. Now, are there any forward forces? So there's no force going forwards, right? There's no force going forwards. So actually that's 0. If there's no forwards force, then the work forwards has to be 0 because there's no forward force in order to do work. But the backward force is our friction. Okay. So 0 take away the work backwards is indeed minus 9.6. So then very simply, we just get two negatives, so we just change it to a positive. So therefore the work backwards is indeed then positive 9.6. So no need to be scared about the negative, it all works out fine in the end. And that being joules. Well, that's the same as the work backwards, because the backwards force is the friction. That is the work done by friction. Okay, so work by friction is indeed 9.6 joules. So there we are. Okay. And then in part C, then it's asking me to calculate the coefficient of friction. So you should also remember that the friction F is equal to the coefficient of friction mu times the reaction force R. So remember, the reaction force is the top force like this. Okay, and also note we have weight. Okay, now weight is mass times G, so it's 0.4. I'll calculate it here. Weight is 0.4 times G, which is 9.8. If we work out the weight force then, which is downwards, that's 3.92. So I'll add that on. Okay, newtons there. Okay, so in order to work out the coefficient of friction, where did I do it? F equals mu R. I need to know my friction and my reaction. Okay, so this is where we're going to need to do a bit more stuff. So we worked out the work by friction is 9.6, but hang on, didn't we discuss that the work done by friction is also the friction force times 7, right? Force times distance, right? So there are two ways we can work out work. We can use the standard formula of force times distance, but also now this energy principle. We've got two of the same thing, so that means F times 7 has to equal the work done by friction, as we worked out to be 9.6. Therefore, we've got our friction value, if we divide by 7, be 1.37 newtons to 2 decimal places. Okay, but now I've got the F, I need to work out the R in order to work out mu. Okay, well, I can then just resolve the forces, right? I can consider the vertical forces, the up and down one. So if I now resolve upwards and downwards, well, firstly, my upwards force in my diagram is my reaction force. Take away the weight, which we worked out to be 3.92. Okay, and so that's mass times acceleration. So what I'm doing here is F equals ma. Okay, force is mass times acceleration. So the mass is 0.4 4, was it? Yes. But then there's no acceleration. There's no acceleration upwards or down. Okay. So simply that goes to 0. Okay. So very simply then, we can say that R is indeed 3.92. Great. Now we know what F and R is. So therefore, we can say that if F equals mu R, we substitute the numbers in, that means that 1.37 for F is going to be mu times 3.92. So therefore mu, if we divide by 3.92, we get 0.35 to 2 decimal places. And there we are. Cool. So it's a bit more a complex question. Yeah. Again, there's quite a few moving parts here, but hopefully all the steps make sense. Perhaps spend some time to go over what I've done there. But hopefully the steps make sense. Okay. Um, Okay, so then we've got this question here. So here I'm told a box of mass 3 kilograms is projected from point A across a rough floor with speed 6. The box moves in a straight line across the floor and comes to rest at point B. The coefficient of friction is 0.4. I'll make a note of that. So mu, the coefficient of friction is 0.4. Work out the kinetic energy lost. Okay, so again, if I just draw the situation on first. So I've got a sort of flat surface, a flat line like this. Then I've got my box, the mass is 3. Okay, I'm also told some speeds. I'm told it is projected from point A with speed 6. So initially the speed is 6. And then at point B, it then comes to rest. So again, that means the speed goes to 0. So it stops moving, okay? Right. I think that's everything I'm really told. I'm not going to consider. We know there's going to be friction. Well, it mentions it, coefficient of friction. So again, that's going to go opposite. It's going to go backwards. I'll call that F for friction. There's not going to be a force forwards. Okay, no force forwards. You might be a tad bit confused about the language here about projected. That doesn't mean there's a force. That means you can kind of imagine it as like kicking it. So if you imagine a kick, uh, initially it's given some force to move it forward, right? Like a kick, like a football. But then it'll slow down because there's no consistent force moving it forward, right? So there's no force forwards, okay, essentially. So that's pretty much everything I can for now. So it's asking me to calculate the kinetic energy lost. So the change in kinetic energy, because that's effectively what it's asking me to do. To work out the energy lost, to work out the change in it. But the change in kinetic energy, well, we know the final speed is 0, so it's going to be half lots of 3 for the mass, 0 squared. That will go to 0. Take away the initial kinetic energy, which is speed 6, so a half of 3 times 6 squared. We work that out. That's going to be minus 54. Again, it's going to be a negative because it's lost the kinetic energy, so it's a negative change. So therefore, loss in kinetic energy is simply 54 joules. Okay, and there we are. And again, that's because the speed has gone down. Okay, and so then in part B, then it's asking again, very similarly, to write down the work done against friction. Okay, so again, if we was to just use the standard formula we saw previously, the work done by friction or against friction, whatever, almost pretty much the same, it really, computationally. So the work done by the friction force, okay. Work done by F, the friction force, that's going to be the force times distance, right? It's going to be F times the distance, which is... They've not told me that, actually. So we don't know either, which is very, very unhelpful. So we obviously can't proceed by using the formula. So to work out the work done, we then need to consider the work energy principle instead. So again, the work energy principle is that the changes in both the kinetic and the GPE has to equal the overall work. Okay. Well, of course, the change in kinetic energy, again, it's minus 54. The change is negative. Okay, negative 54. And then obviously there's no GPE here because it's always on the floor. So no change there. And then and then that's going to equal the overall work, right? Now, the overall work, again, the overall work is going to be the work done forwards. I'll include it here. Work forwards, take away the work backwards. So the work done by forwards force, take away the work done by the backwards force. Okay. Okay, now of course there is no forwards force. Okay, so that's going to be 0. And then minus the work backwards, that's going to equal minus 54, right? But then very simply then we can therefore get the work backwards is just 54 joules then, right? The negatives cancel. And so therefore, because the backwards force is indeed the friction, the work done by friction is this backwards. So work done by friction is 54 joules. Okay. And so there we are. Okay. Then in part C, then it's asking me to calculate the distance AB. So in other words, it starts at point A and ends at point B. So in other words, it wants the distance travelled. Okay. Okay. So that's going to link into this work done formula, the force times distance, right? Because now we know what the work done is by the friction. Okay. So work done by friction by F is again force times distance. We know that the work done is 54. That's going to equal force times distance. So I'm going to need, if I want to work out the distance, I'm going to need to find the force F. Okay. Now, we know what the coefficient of friction is. We also know that the formula involving that is F equals mu r, right? So that means F is going to be, well, mu is 0.4. Friction is 0.4 lots of R, the reaction force. I'll add that on. Okay. There. Squeeze it in, the reaction force. Then I've got a weight. Now the weight is going to be, again, 3 times G, or 3 times 9.8. Mass times G. And that will get me 29.4. So 29.4 newtons. So then again, if I then look at the upwards and downward force, resolving that, well, the upward force is the reaction, take away the downward force of 29.4. Again, that's going to equal mass times acceleration, but there is no acceleration up and down, so it equals 0. So very simply, R is 29.4. So therefore, I can now find friction. So that means friction is 0.4 times 29.4, which will get me 11.76 newtons. Okay? Okay, so we're nearly there. So now we can look at this formula again. And say that 54. In fact, I'll get rid of this now. That 54 is equal to F, which is 11.76 times D. Therefore, D, the distance is 54, divided by 11.76, which gets me 4.59 meters to 2 decimal places. And there we are. That's the distance from the 2 points. Okay, cool. Okay, so we've got this question here. It's a very interesting question. It brings basically everything together and it makes full use of the work energy principle. Okay, so let's take a look at it. So here, we're told a skier moves downhill from point A at 6 meters per second. After descending 50 meters, the run begins to ascend. When the skier ascended 25 meters to point B, his speed is 4. The skier and the skis have combined mass of 55. The total distance you've travelled from A to B is 1400 meters. The non-gravitational resistances to motion are constant, have total magnitude of 12 newtons. Calculate the work done by the skier. Okay, there's a lot of stuff there. Okay, but helpfully they've drawn a diagram to show what's going on. Okay, right. So essentially, what's happening here is, as you can see, we start at this point here, and we have a starting speed of 6, and she ends up here, the skier, and then the speed goes to 4. Okay, so we've got these 2 points again, A and B, but this time there's gravitational energy involved because it's above ground. We've got this ground level here, as you can see, sometimes called the 0 level. Okay, um, and so we can see that initially she's 50 meters above ground, and at the end she's just 25 meters above ground. So there's going to be a change in kinetic energy and a change in gravitational energy. So actually, let's just start with just working those things out. Right? Let's keep it simple, break it down. So firstly, the change in kinetic energy. Well, that's going to be the final at the end. So it's going to be half mv squared. Well, we know the half the mass is, we're told is 55. So it's going to be half times 55 times the final speed, which is 4 squared, and take away from the initial kinetic energy. So that's going to be half of 55 times 6 squared. That's the initial speed. If we work all that out, um, we get minus 550. And again, it's a negative change because the energy is lost simply because the speed has gone down from 6 to 4. So loss in kinetic energy there. Then we calculate the change in GPE. Okay. So that's going to be mass times mass, which is 55, times G, which is 9.8, times the height. Okay, well, we can do the final GPE. At point B, she's only 25 meters above ground. Okay, so if we work that out and then take that away from the initial GPE, kind of like kinetic energy, right? Well, the height is 50 meters above ground, so it's going to be m, which is 55 times 9.8 times 50. So if we work that out, that's minus 13475. Okay. And again, that's also negative because overall, between the 2 points, she's gone further down because she starts 50 meters above and then she's just 25 meters above ground at the end there. Or what you could do it sort of in one step. Instead of doing these 2 different calculations, you could say that the change in GPE is again going to be mass, which is 55, times 9.8, times the height. Now, the height, you can calculate the change in height. So, so at the end, she's 25 meters above ground, but at the start, she's 50. So the change is 25 take away 50. And and then you'd get the same answer, right? Minus 13475. So you could do it that way. You could literally split it into two different parts at the finish and at the start, or you could do it that way. Anyway, so we've got our two changes in kinetic energy and gravitational energy. Okay, they're both negative again because you lose speed and you lose height. Right. Now, if we then consider the work energy principle, the change in kinetic energy plus the change in GPE, that's going to equal the overall work. Okay. So hopefully with me up to here, all I've done here up to now is just calculate the changes in the kinetic and the gravitational energy. Okay. With the speeds and the heights given. Okay. Hopefully with me up to here. Okay. Now, as I said, this is the work energy principle. Now I can just substitute these numbers in. So we know that the change in kinetic energy is again minus 550. Again, minus as it's a loss. We lose it, and then the change in GPE is minus 13475. So that's my overall work. Okay. Now the overall work again is the work forwards. Oh, take away the work backwards. Okay. So the work from a forward force, take away the work of a backwards force. Okay. Now, I'll rewrite it. I'll simplify this. Work forwards minus work backwards equals if I do minus 550 minus 13475, I get minus 14025. Okay. Now, we are told some stuff about the force of non-gravitational resistance to motion. Okay. So, and they've asked us to calculate the work done by the skier. Now, what's happening here is, again, if you just picture, we've got the skier, right? This time it is a forward force. The skier is sort of producing a forward force to move the skier forwards. But then there's a resistance force acting obviously the other way to resist the motion. Okay, hopefully that makes sense. I know for sure there's a force forwards because it's asking me to calculate the work done by the skier. So the skier moves forward, right? Anyway, but we know we know the what's it called? We know the force of the resistance force. We know the resistance force is 12 newtons. So what we can do is we want to work out the work forwards, right? So actually, if I sort of simplify this even more, work forwards is going to equal by adding on the work backwards. Take away 1425, right? Okay. Now I just need to work out the work backwards because then when I do that, I've got the work forwards, obviously. Okay. Now the work backwards. Okay, that's going to be then we're going to resort to using our standard formula, force times distance. Now we know the backwards force, the resistance is 12. Okay. But we also know the distance the skier travels. They told us from the total distance from A to B is 1,400. So there we are. Okay. Do not get confused by these heights. The heights, not the actual distance travelled. Okay. So actually, we got the work backwards. Okay. To be 16,800 newtons. That'd be joules. Sorry, joules. Okay. So there we are. So now we can simply substitute it into what we've got here. So the work forwards is going to be 16,800, take away 1,425. If we work that out, that's going to be 2,775 joules. So that is the work done forwards. That's the work done by the forwards force. So that's the work done by skier. Skier is doing forward force. It's pushing the skier forwards. And so there we are. Quite a complex question again. It adds everything together into one there. So it's quite an interesting question. It brings everything together in one there. Okay, again, make sure you read that and make sure every step makes sense there. Okay, there's a lot going on there. Okay. Okay, so we're going to look at an exam question before we look at the last part. Okay, so here we're told a stone of mass 0.5 kilograms is projected vertically upwards with speed u from a point A. The point A is 2.5 meters above horizontal ground. Speed of the stone as it hits the ground is 25 meters per second, and blah 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 blah. So waffle, right? So it says in part A to use the model and the principle of conservation mechanical energy. So conservation of energy, just in fancy language, to find the value of this u here. Okay, so it's very wordy, but in essence, it's the situation isn't that complicated, and it's actually telling us what to use conservation of energy. It's quite nice. Okay, so what's happening is we have this stone that's shot upwards. Okay, projected or kicked upwards, if you will, whatever, right? It moves upwards. So what's happening is we have this little stone here. The speed is u. Okay. And I'm also told at this point A, this this point, it's 2.5 meters above ground. So we have a ground, and the height above this ground here is 2.5 meters. Okay. And then I'm told the speed of the stone as it hits the ground is 25. So what's happening is, obviously, the stone will move up, and then it'll come back down to the ground. So when it hits the ground, the speed we're told is 25. Okay, and there we are. That's pretty much everything. Okay, and so we know it won't be work energy principle here because there are no forces acting on the stone, obviously apart from gravity, but there's no forces we need to consider here. So it's just conservation of energy. Okay, no friction or anything like that. Okay, so conservation of energy. Remember what that says is that the gain in energy is the loss in energy to conserve it, right? So if we gain any energy, we have to take that back. So we have to lose it as well. Okay, so we know it's kinetic. We know we deal with kinetic energy and potential energy. Which energy are we going to gain and which one are we going to lose? Okay, well, obviously we don't know the initial speed, but what we do know is the height. We know that we lose height, okay, because at the end, when we end up on the ground, well, we go down by 2.5 meters, so we lose height. So the loss is going to be from the GPE. So if we calculate the loss in the gravitational energy, that's going to be mgh. Well, we know that the mass is 0.5. And then G is 9.8, and the height, well, we know that is 2.5. Okay, and so if we work that out, that's 12.25. Okay, now, now we don't need to worry about the sign. It would be a negative because we are losing it, but we already specified it's a loss, so we don't need to care about the sign. We know that the loss in energy is just simply 12.25 joules. Okay. Now, the change in GPE would be negative. 12.25. Remember, the wording is important here. If I'm telling the loss, I already told you it's a loss, right? But the change is a negative change, okay? So that matters, okay? The change in gravitational energy is minus 12.25, but the loss is just 12.25 joules, okay? I know it's a very slight difference, but there we are. Now that's the loss in gravitational energy. So according to this conservation of energy, we need to gain that back in kinetic. So gaining kinetic energy has to be 12.25 as well. But we also know that we also have the two speeds. Well, we know that the initial speed is this u, but we know the final speed is 25. So then we can also say that the gain in kinetic energy, that's going to be a half times, well, the final speed, that's going to be, the mass is zero 0.5, so half times 0.5 of 25 all squared. Take away the initial speed, which is u, so it's just going to be half of 0.5 times this u squared. Again, that's going to equal 12.25. Okay, so that's my change or my gain in kinetic energy here. Okay, so we just work all this out, then that's going to be half of 0.5 times 25 all squared. Going to be 156.25. Take away then a half times 0.5 is 0.25 u squared equals 12.25. We just solve this for u now, right? So it's a simple equation to solve. So 0.25 u squared, that's going to be 156. Take away the 12.25. That's going to get me 144. Okay. Then if I divide that by 0.25, I get 576. So therefore that means u, if I root that, I square root that, I'll get 24. Quite nice. Okay, and that's my u. Okay, and we can confirm our answer makes sense, because if u is 24, well, if the speed is 24 and then it ends at 25, indeed, that gives me a gain in kinetic energy, which is what I expect, because the speed has increased from 24 to 25, right? So indeed, we do get a gain in kinetic energy, so that all makes sense. Right. Then part B. So we're told in reality, the stone will be subject to air resistance as it moves from this initial point A to the ground. State how it affects your answer to part A. Okay, so bear in mind what I answered was the value of u. I found the value of u. What this is saying is if we add air resistance and we only change the value of u, right, the start speed, if I only change that, everything else stays the same. Okay, so the heights stay the same and the final speed stays the same. The only thing we're changing to accommodate for air resistance is the value of u. So to allow for that, do we increase or decrease the value of u? Well, when I think about it, air resistance, well, it's a force. So obviously that's going to take some of the energy. Air resistance will try to slow you down naturally, right? So in order to overcome that, you're going to need to increase this speed here, because then that will give greater kinetic energy, right? To then overcome the air resistance. So if you want to still make sure the final speed is 25 and the energies make sense, you're going to need to increase the start speed to accommodate for the energy to be sucked up from air resistance. Okay, so hopefully that made sense. So we need to increase u, because air resistance will slow me down and take away some of the energy. So I need to increase the energy, increase the speed to account for that. Okay. So the value of u would increase. Okay. and that's really all they're looking for. Uh, okay. I guess you could say as air resistance. You don't have to, but the idea is air resistance would slow you down and require energy to overcome, right? And so there we are. Okay. Quite a weird question. You get those in normal maths as well, but that's the idea. Okay, now we're told the ground is soft and the stone sinks a vertical distance d into the ground. The resistive force on the stone by the ground is modelled as a constant force of 2000 newtons. And now we're told to use the work energy principle, which is different to the conservation of energy, which we just used. Find the value of D. Okay, so if I sort of draw this situation now, so we've got a sort of slightly different situation. So what's happening is this stone is going through the ground. So I'm guessing it's some sort of mud or something. So it's it's D centimeters above ground into the ground, right? Okay. Um, so say this is my ground. Um, we start here and then we end D. Okay, my distance, my height, which is actually called D. Okay. I picked up the units. It's in centimeters. That's an issue. Okay, because it has to be in meters. But we'll deal with that as it comes. But that's in centimeters for now. Always pay attention to units. But there we are. Okay, so uh, we know that the speed going into the ground is 25. So that's sort of my initial speed now, 25. So that's when it hits the ground. But then after it goes underneath the ground by D, right? Then has some other speed V. Okay. Um, Actually, no, we know no after it sinks. So eventually it'll go to zero speed. Actually, so we know the speed at the end is zero. Okay, and it slows down. It goes. It comes. It slows and stops there. Okay. Right. And that's really everything. But what we need to use the work energy principle because now there's a force added on. We've got this resistance force of 2000 newtons, okay? We need to bear that in mind. So what it tells us to use the work energy principle. So that's going to mean that the change in kinetic energy, add change in gravitational energy has to equal the overall work. Okay. Now, let's work out the changes in these two energies. So firstly, changing kinetic energy. Okay, well, we know at the end, the speed is zero, so it's going to be zero take away half mv squared. Speed at the start is 25, so half times the mass of 0.5, I believe. Yes, times 25 squared. That's going to be 150 minus 156.25. And again, it's negative because you lose kinetic energy. Okay, I'll make a note it's a loss. Okay, but I do need to keep the sign. Okay, the negative. Okay, then the change in GPE. Okay, well, it's a bit of a funny one. This is because obviously it starts on the ground, but actually we go underneath. So technically, this is sort of my ground level now, if you will. So the change in the change in gravitational energy, well, that's mgh. So the mass is 0.5, g is 9.8, and the height, well, we've gone down by d. Now this has to be in meters. So remember that if well, you should know 1 meter is 100 centimeters. So to convert to 1 meter, centimeter, sorry, it's 0.01 meters if you divide by 100, right? The units matter because it has to be in meters. So that's simply going to be 0.01 d lots of meters. Okay, so the height in meters is 0.01 lots of d. Okay, because it has to be in meters. Done. Hopefully that made sense. The units do matter, has to be in meters. So it's not d we've gone down by, it's 0.01 d. That's what we're going to use. And it's going to be a negative because we've gone down by that amount. Okay, so the change in GPE is going to be negative 0.049d. Okay. So therefore, if I substitute that into my work energy formula here, that's going to mean that minus 156.25 minus 0.049d has to give me the overall work. Okay. And so the overall work then, again, overall work is the work forward minus the work backwards. Now, there is no forward force. We're only told here there's a resistive force, so resistance. So it's going to oppose it. So it's going to go work backwards. So there's no work forwards because there's no forwards force moving the stone forwards. So work forwards minus work backwards. That's the overall work done. So that's going to be 0. And then the work backwards, well, we do have a resistive force, so that's backwards. So that's going to be force times distance. So the resistive force is 2,000 newtons. And again, the distance, well, that's going to be the same 0.01d. Okay. And that's going to equal minus 156.25 minus 0.049d equals 0 take away 2,000 lots of 0.01d. Now we just get an equation to solve for d. Okay, so if I simplify this, okay, now I just solve this for d. I get 19.951d has to equal 156.25. Therefore, d is going to be 7.83 to 2 decimal places. And there we are. That is the value of d there. Oh, to 3 significant figures. Oh, that's the same thing. 3 significant figures. There we are. Cool. So there we are. Okay. We're now going to look at more problems, but now even harder. We're going to look at inclined ground. So these are when it's at an angle, right? So in this question here, we're told a package of mass 5 kilograms is released from rest and slides 2 meters down a line of greater slope inclined at 35 degrees. Okay, so we've got this setup here, right? So it's at an angle of 35. We've seen problems like this already. Okay, so we've got this package. So I'm going to say this box here, 5 kilograms. Okay, and I'm told it's released from rest. So initially the speed is 0. Oh no, sorry, it's going to go down the slope. It moves down the slope. So it starts up here at 0 speed. And down the slope, the speed doesn't tell me the speed when it moves down the slope. I'll just call it V. So I've got these two speeds again, right? So let's say the box is up here and then it ends up down here, right? That's the idea. It moves down the slope. Okay. It wants me to work out the potential energy lost, first of all. The potential energy. Okay. So we know that the loss in GPE, the potential energy, again, is mgh. Okay, so we know the mass is 5, we know that G is 9.8. However, the height, okay, it's going 2 meters down the slope like this. However, that is not the vertical height. This is the height that I'm interested in. How do I work that out? Well, we can look at this triangle here. So if it's 2 meters down the slope, let's say 2 meters there at the angle 35, then we want this vertical height here. Well, we get a right angle triangle and then it's SOHCAHTOA, so we can work out the height using SOHCAHTOA. Well, it's opposite, the height is the opposite side, so the height h is going to be 2 times sine 35. Okay, so if we work that out, that's going to get me 1.15 meters to 2 decimal places. Okay, there we are. So that is my height. That's my vertical height. Okay, so times that by 1.15. So the loss of GPE is going to be 56.21 joules. Okay, to 2 decimal places. Okay. Again, we could make it a negative, but the idea is at the end of this is the loss, right? And it is a loss because we're going down the slope. Okay, we're going downwards. So there we are. Then in part B, then it's asking me to write down the kinetic energy gained. Okay. Now you'll notice the language right down. It's kind of saying you don't need to work anything out. You should already know it straight away, right? So it's asking me to work out the gain in kinetic energy. Now, there is no forces acting on this box here. There's no friction mentioned. There's no driving force. There's no force forwards because it's just moving down due to its weight, due to gravity. So there's no actual forces really acting on it. So it's just conservation of energy. So that means because we're losing GPE, it has to match the gain in the kinetic energy. Okay, and I'll make a reference. It's conservation of energy. Okay, you don't need to write that application, but that's what we're using. Okay, so hopefully we've been there. So it's simply the gain in kinetic energy equals the loss in GPE. Okay, that's conservation of energy. Okay, and so very simply, that also is 56.21 joules, and there we are. That's literally it. Okay. Then in part C, it's asking me to work out the final speed of the package. It's speed V, where it ends up after 2 meters. Okay, so we know the gain in kinetic energy, but we can also work it out by doing the final minus the initial kinetic energy. Well, the final kinetic energy is going to be half mv squared. Well, the mass is 5. So it's going to be 5 times v squared minus the initial, which is half times 5 of, well, it was at rest, right? So at rest, so it had no speed. Yes. So simply, that's just going to be 2.5 v squared. And that has to equal this 56.21 because they're the same, right? And so therefore, v squared, if we divide by 2.5, I get 22.484. So if I square root that, I get v to be 4.74 meters per second. And there we are, 4.74. Cool. So there we are. And so make sure you're confident in how we can work out the potential energy and the kinetic energy. We looked at this last time, but you really need to be confident because they love asking questions. As you'll see in a moment, we're going to look at some exam questions. They love asking about slopes, just to make it as hard as possible. So hopefully you understand the steps there. Okay. Right. So we've got this question here. So we're told a smooth plane is inclined at 30 degrees. So immediately you can start to like jot down and draw the situation. So 30 degrees. We got a particle, mass 0.5. Again, we've got this little box then, 0.5 kilograms. It slides down, so it's going to move downwards. Okay. We start from rest. Starts at rest. So initially has no speed, and then it passes a point with speed 6, so then it ends up at 6 meters per second. Okay. Find the distance AB. Okay, so if I say that's A and then I don't know, that's B. What is this distance here? Okay. So in other words, what's the distance travelled essentially? Okay. Now, what can I do here? Well, firstly, again, there's no forces. There's no friction because I'm told it's a smooth plane. So I remember I mentioned rough means friction. Smooth means no friction. I'll make a note of that. Okay, if you're not aware of that already. So there's no friction force. There's also no force pulling it forward apart from its gravity, apart from weight, right? I'm not told about any forces like that. That's it. So there's no forces really acting on it. So it's conservation of energy. No, so I need to work out. So I know that the gain in energy is again equal to the loss in energy. So which am I gaining and which am I losing? Well, I can just look at the speeds, right? Well, quite nicely, I know that the speed is increasing from 0 to 6. So I'm gaining kinetic energy. So in other words, the gain in kinetic energy has to then be the loss in GPE. And that makes sense because I'm going down the slope, so I'm losing height. Okay, so let's work out these two things. So gain in kinetic energy. I know my speed, so the gain, well, the final speed is 6, so that's going to be half times the mass, which is 0.5, times 6 all squared, take away half of 0.5, up to 0 squared. So if we work that out, yeah, that'd be 9 joules, and so that's my gain. And there we are. So that means the loss in my GPE has to also be 9. Okay. But I can start to work out an expression for the GPE because it's asking me for distance here. Okay. I also know that's going to equal mgh, right? So so that means 9 is going to equal mgh. The mass is 0.5. G is 9.8 times h. Okay, but I can work out h from this, right? I can work out a vertical height. So 9 divided by 0.5 times 9.8. H will get me 1.837 meters to 3 decimal places. That's h, my height. Okay, so that's going to be this height here. Okay, height is 1.837. Okay, but it wants 1.837, but they've not asked me for the height. They've asked me for the actual distance down the slope. Okay, so again, I'm going to use that sort of triangle I used before. So if I'm going down, if I call the distance x, right, that's the distance physically moved down the slope. Again, it's angled at 30 degrees. But I do know this time my height is this 1.837. So therefore, again, I can use SOHCAHTOA to work out x, my hypotenuse. It's opposite. So I'm going to use sine. So SOHCAHTOA. So that means sine 30 equal 1.837 over x. Therefore, x is going to be 1.837 divided by sine 30. Now, if I work that out in the calculator, I get 3.6 x7 meters to 2 decimal places. And there we are. That's the distance travel. Okay, there we are. Cool. So hopefully you can start to spot a sort of like general sort of method here now, right? Working out the change in energies and then work out any missing stuff from there. Okay, so have a look at this example. So we're told a particle mass 2 kilograms is projected with speed 8 up the slope of a rough plane, inclined at 45 degrees. So again, we've got the situation. We've got 45 degrees. Okay. Again, we've got this parcel, 2 kilograms. Now it's going up the slope this time. So it starts with speed of 8. Then it ends up before coming to rest. So it ends up with 0 speed. Okay. And it's asking me to calculate the distance it travels, essentially, right? Now, I'm also told the coefficient of friction is 0.4, so mu is 0.4. So, spoiler alert, there's now friction involved. And I know for definite there's friction because it's a rough plane. It's that means it has friction, okay? So, if it's going to go up the plane, there's a friction going to oppose it like this. Now, there's not a force pulling it forward. Well, there's no reference to it, but also it's projected. So that means it has like an initial kick up the slope. Okay. So there's no actual force applied to it throughout the journey. It's just a literal kick up the slope. So the only force acting on it really is the friction. If that makes sense. Okay. Okay. So that's going to require the work energy principle. So that's going to be the change in kinetic energy plus the change in GPE is going to equal the overall work. Okay. So firstly, the change in kinetic energy. That's quite simple because we know the speeds. We know it starts at A and ends at 0. So the change in kinetic energy, well, the final kinetic energy is 0, so it's going to be 0 take away half of the mass, which is 2, times the initial speed, which is 8 squared, and so that would be 64, minus 64 there. Negative because we're losing kinetic energy. That is important, that negative. Then the change in GPE, and that's going to be mgh. So my mass is 2, G is 9.8, and the height. Okay, well, again, I want to work out the distance. So, I want to work out this distance here. Okay, how far have I gone up the plane? Okay, I'm going to call that distance x. Okay, x meters. That's what I want to work out. But in order to consider the GPE, I need the height. Okay, this is where there's going to be a bit of algebra involved. Okay, so again, I'm going to construct a little triangle to help me work out the height I want. So again, the angle is 45. The distance travelled up the slope is x, so I'll go up by x. I want my height h. So that means, again, if you SOHCAHTOA, h, which is the opposite, is going to be x times sine 45. It's going to be in terms of x. So that means sine 45 is root 2 over 2. So h is root 2 over 2 lots of x. Okay, so h is root 2 over 2 lots of x. If I simplify this, it's going to be 49 root 2 over 5 x. and that's going to be positive because we're going up the slope, right? We're going up, so it's positive because we're going up in height. Okay, cool. So then that means if we then look at our work work energy formula, I'll box it here. So the overall work is going to be these two changes in energy. So minus 64 at 49 root 2 over 5x. Okay. But of course, the overall work is then split up into the work done by forwards force, take away the work done from backwards force. As I discussed, there's no forwards force. The only force is the friction, which is acting backwards. So actually, if we split this up into work forwards, take away work backwards, that's about going to be minus 64 and 49 root 2 over 5x. Okay, well, there's no forward force, so there's no work in the forward force, right? But the work backwards, well, it's the force F, right? So it's going to be F, so force times distance. So that's going to be force F, and the distance is X, right? That's what we want to work out, the distance. So it's going to be Fx, and that's going to equal minus 64 at 49 root 2 and 5x. Okay, so it's looking quite ugly, but if I want to work out X, I need to find F, okay? But this is where this coefficient of friction will help me, okay? So, I know that F equals mu r. Now, now there's going to be a reaction force over there. If I get rid of this here, remember there's going to be a weight. Now that's going to be 2g. Now 2g, or 2 times 9.8, that's going to be 19.6. Okay. Now remember, specifically with at an angle, we need to split it up like this. Okay. So it matches the reaction force, and this is going to be 19 point, and so this angle is 45. So this is going to be 19.6 cos 45, and this is going to be 19.6 sine 45. Okay. Now we're going to want to resolve. We're going to want to look at the forces perpendicular, so in this sort of direction. So the force upwards is R. Take away the downwards force, the opposite one, which is 19.6 cos 45. Okay, and there's no acceleration in this direction, so it's just equals 0. That means R is equal to 19.6 cos 45, my reaction, which simplifies to, if I times by cos 45, I get R to be 13.86 newtons there. Okay. Okay, so now I can look to use F equals mu R. I'll do it down here. So mu is 0.4. I know what R is, so that means I can work out friction, which is 0.4 times 13.86. And so that's going to get me 5.54 newtons. And there we are. Okay. Now I can use that here. There we are. So that means minus 5.54 lots of x is going to equal minus 64, add 49 root 2 of 5x. I'm just going to round that as well. We'll get away with that. So 49 root 2 of 5, because we've already done some rounding anyway. So there we are. We'll be fine with that. 13.86x. That's what that fraction goes to. To two decimal places. Okay, so here we are. So now it's quite a nice looking equation we could solve for x. So that means if we so 19.399x equals 64, so that means x is going to be 3.3 meters to 2 decimal places. And there we are. That is x. That was the distance between the two sort of points, right? The two parts there. Okay, there we are. So there's a lot there. Okay, that's the thing, right? There's a lot of steps here, but it's sort of just pretty much the same thing every time. So once you are comfortable with the steps, hopefully you should be set up quite nicely. And right, we're going to look at some exam questions now, and you'll see again there's going to be a lot of slopes and stuff like that. Here we are. So we've got this question here, and I'm given a diagram, and we've got a ramp. We're told that sine theta is 2/7. We've got a parcel of 4 kilograms, which is projected up the slope, up the ramp. So again, if I just sort of jot what's going on, then I know they give me a diagram, but I'm just going to draw a bigger one by myself here. So we've got theta. Again, I got this little box. It's 4 kilograms. What speeds am I given? Well, I start speed 5. Okay, that's my initial speed, and then it goes up the ramp. And then it says it first comes to rest. Okay, so it comes to rest. So it means it goes to 0 speed, and I'm told the distance between these 2 points is 2.5. Okay, so I'm making note of that. I'm also told stuff. I'm also told here information about resistance. So there's going to be a resistance force. So that's going to be acting. So if it's going to move up the plane, it's going to act down like this. Okay, and I'm told it's R, just R, which is quite unhelpful because normally that's the reaction force. But anyway, I'm told the resistance, sort of like the frictiony force, is R. Yeah. Okay, and that's really all I can add on. I'll only add on the forces if I need to. Okay, but that's the bare bones diagram. Hopefully you're with me here. That's setting up the question. Okay, so I need to show that R is indeed this 8.8. I need to find R then. Okay. And it's told me again to use the work energy principle. So it tells you what to do, which is quite nice. So we know it's going to be work energy because now, indeed, there is a force acting on the object, right? There's a backwards force. Okay, so again, the work energy principle. That's going to tell us the change in kinetic energy plus the change in GPE is going to equal the overall work, right? Okay. I'm going to probably actually do this in one go then, just to speed it up a bit now. So the change in kinetic energy, well, we know at the end it's 0, so it's going to be a half time. Well, it's going to be a half lots of the mass, which is 4 times 0, and then I'm going to take away the initial speed, which is 5 here, and that's my change in kinetic energy, and then my change in GPE. Okay. So again, that's going to be mgh. So my mass is 4 times 9.8 for g. Then my height h. Now I need to work out the height. I am told the actual distance travelled up is 2.5. So again, my distance up the slope is 2.5. But indeed, I want the actual vertical height here, right? So I'm going to work that out by this triangle here. I'll do it here. So again, if I'm going 2.5 meters up the slope with the angle, I want this height here. Okay. So if I use SOHCAHTOA, the height h is going to be 2.5 sine theta. Now, I do not know what theta is by itself, but what I do know is what sine theta is. That's all I need, because all I need is sine theta here. So 2.5 sine theta is going to be 2.5 times 2/7. And so that will be 5/7. Okay, so h is 5/7 meters. Okay, so times by 5/7, and it's positive because we're going up the slope, so we gain in height, so that's great. And so that's going to equal overall work. Now that's going to be, again, work forwards, take away work backwards. Okay, so if we just simplify this, of course there are no forward forces, so that's good. So work forwards is 0. Take away the work from backward force. Well, we know that the backward force is this R. So if I work that out, the work done by R is going to be force times distance. So R times the distance, which is 2.5. Okay, because again, remember, we're told the distance is 2.5. Okay, and so that's going to equal, if I now just put all that in the calculator, half of 4, so that'd be 0. Take away a half of 4, lots of 5 squared, plus 4 times 9.8 times 5/7. I get minus 22. Okay, so that means minus 2.5 R is minus 22. Hopefully we get 8.8 from this. And we do. So R is 8.8. Great stuff. Okay. Okay, now let's have a look at part B. Okay, now we're told after coming to rest at B, the parcel now slides back down the ramp. The total resistance to motion is still 8.8 newtons. Find the speed when it returns to A. Okay, so it's kind of what's essentially happening here is kind of the exact opposite scenario. Instead of starting at A and ending at B, now we're starting at B and ending at A. Okay, it's kind of the complete opposite scenario. Okay, instead of moving from A up to B, now we're starting at B, moving down to A. So if I now draw this situation on in a new diagram, so what we've got going on now is again the angle theta. I have my parcel. The mass is 4. Okay, now it's moving down the ramp, so it starts at B, right? And we know it starts at rest at B, so the starting speed is 0 as it moves down the ramp. But then it ends up back at A, so it's going to have some speed V. Okay, and that's what I want to work out. It's asking me for the speed when it reaches this point A down the ramp. Okay. So that's the idea. Let's add our forces on. Well, again, we have a resistance force. It's 8.8 newtons. Now, because we're moving down the ramp, that means now the resistance, or sort of the friction force, if you will now would act up like this. Okay, there. Okay, if I need to add on my weight and my reaction force, if I need that, but I don't think I will. But that's basically the diagram, okay, that we're working with. Again, there's going to be no driving force. There's no force mentioned going forwards, okay? Right. So with all of that, then let's proceed to find the speed. So, again, we can consider the work energy principle, right? So again, that's going to be changing kinetic energy plus the change in gravitational potential energy equals the overall work done. So the overall work, okay? Firstly, the change in kinetic energy. Well, now the final speed is v, and we start with 0. So that means the change in kinetic energy is going to be half of m, which is 4, times v all squared. Take away 0, because the initial speed is 0. So there we are. So then the change in gravitational energy, then, right? So again, that's going to involve the vertical height, because remember, the gravitational energy is mgh. We need the vertical height h. Well, of course, we know again that the distance traveled from A to B is 2.5 meters, right? So the distance traveled is still 2.5 meters, but we need the vertical height traveled. So again, to work that out, we can do a little triangle. I will do it. I will do it here very quickly. This little triangle here. So again, we've got the angle theta. Now we're going down the ramp by 2.5. So if it's 2.5 here, then the height h here. Again, we've got right angle triangle. Do a bit of soccer tailway. H would then be 2.5 sine theta. But we also know what sine theta is. It's 2/7, right? So that means it's 2.5 times 2/7. So that leaves us h to be at 5/7. And so there we are. So that means my change in GPE is going to be mgh. Okay, well, we know that mass is 4, G is 9.8, and H. Okay, well, now we're going down. Okay, as you can see here, we're going down the ramp. So the change in height is negative, so negative 5/7 then. Okay, so negative, we're going to be losing GPE because we're going downwards. Okay, so there we are. And so that's overall work, which of course we can split as work forwards, take away work backwards. Right? Okay. Okay, so then if you just stick with this then, actually, if we simplify this, work forwards, take away work backwards. That's going to be half times 4 is 2, so 2v squared. Then if we work out 4 times 9.8 times minus 5/7, we get minus 28. Okay, so now let's deal with the work then. Firstly, as we discussed, if it's going down the ramp, there's no forward force on the object here, because the forward force will be here, but there is no force forward. So in the direction of motion, there's no forward force. So actually, there's no forward force. There can't be any work back forwards. And then minus the work backwards, so the backward force, the force resisting, well, we know it's 8.8. So then remember, so if I just do it quickly here, the work backwards is gonna be again force times distance. That's my work formula. Okay, so my backwards force is again this 8.8, so 8.8 for the force times distance, which is 2.5. That's how far removed. We can work that out to be 22. Okay, and so my work backwards is 22. So subtract 22 here to equal 2v squared minus 28. Okay, and so actually then I could solve this for v, which is what I want. So that means then that 2v squared minus 28 is negative 22. Therefore 2v squared is going to equal 6. Okay. Therefore v squared is 3. And so if we square root that, we get that v is 1.73 meters per second. Okay, and that is my final speed. that I want. Cool. Then in part C, it's asking us for 2 improvements that could be made to the model. Okay, I'll do that up here. So these are, so there's I guess there's 2 sort of like stock sort of answers perhaps. So 2 improvements that could be made to the model to give a closer answer. Well, first of all, sort of one common sort of reason is the fact that this sort of the resistance force, right? The resistance force is constant. I highlight it here. That means it never ever changes. Now, in reality, do you expect like friction to always be the same? If you think about, for example, driving a car, you can expect more friction if you drive it really fast compared to going really slow. So in reality, you should expect the resistance to change. So the resistance force should vary. Okay. So that's one improvement. The there we are. Then that's the first one. Then the second one is that we used G. You know, when we talk about the GPE to be MDH. So G, technically again, G is like a really large decimal. I'll see if I can find it quickly. Value. It's here. So the actual number for G is 0.80665, but we never use that whole number for G. Okay, so naturally, when we round it to 0.8, right, that's what we use 0.8. But actually, this is the full answer for G. So actually, there's naturally a bit of rounding, which actually ever so slightly makes our answer a bit inaccurate, ever so slightly, right? A bit of rounding error, if you will. So, what you could simply say is use a more accurate value of G, because then that will give you a more accurate value for the gravitational energy. Okay. Um, okay. And there we are. Those are the 2 sort of answers you can pretty much use. But yeah, you do get those sort of questions sometimes. So there we are. Okay. So now we've got this question. So here we told a particle of mass m, it's projected with speed 5 meters a second down a slope. The plane is inclined at an angle. Again, if we sort of draw the situation, then we've got a surface like this. We've got an angle alpha. Okay. So again, then I've got this sort of object. I've got my what we call particle. The mass is m. So I'm just going to say m. You don't know the number, so it's just m. Okay, kilograms, and it's projected down. So that means, well, it starts with speed 5, and it's going to go down like this. And what we're asked for is the speed when it moves 8 meters down. So when the distance is 8, what is the speed? What's the final speed after 8 meters down the slope? Like this. I'll call it V again, right? V. I'm also told, again, there's going to be a resistance force. Now, again, if it's moving down the slope, the resistance will go up the slope like this. And I'm told the force is a fifth, lots of mg. Okay. So there's a little bit of algebra here with some unknowns. There's an m. Okay, I'm not gonna I'm not gonna convert G to 9.8 right away. I'm gonna leave it there. But hopefully you understand this diagram here. Don't get put off by the algebra, the m's and all that. Okay, hopefully you get the main idea here. It's the same as what we've done previously, or the last few examples. Okay, that's really it. So we're going to use the work energy principle. So once again, the work energy principle, changing kinetic energy plus the change in GPE is going to equal overall work. Okay, So if I work out the change in kinetic energy, um, the final kinetic energy is going to be this V, so it's going to be half mv squared. So half, and the mass is m, so it's mv squared, literally just that. So half mv squared is the final, and the initial energy at the speed is 5, so it's going to be half times m times 5 squared. Okay, and there we are. Then the change in GPE. Okay, that's mgh, so it's going to be mg times h. So again, that's going to be the vertical height here. So again, if I do a little triangle to sort of work that out. So again, I know my distance is 8 meters on the slope. So I want this height h here, the angle's alpha. So again, if we use SOHCAHTOA to work out the vertical height h here, that's going to be 8 sine alpha. Now, I know what sine alpha is. I don't know what alpha is, but I don't need to. I know what sine alpha is. So that's going to be 8 times 3/5. So if I work that out, that's going to be 4.8 meters there. And that's so times by 4.8 here. Okay. Now that's going to be negative because we're going down the slope. Okay. So that'd be minus 4.8. Okay. Then that's overall work. So it's going to be work forwards. Take away work backwards. Okay. Now, obviously, once again, there are no forward forces, right? So there's no force that way here. So the work forwards, because there's no forwards force, there's no work forwards. So it's going to be 0, take away. Now, the work backwards, we do have a resistance force acting backwards to motion. So it's going to be the force, which is a 5th mg. So it's going to be force times distance. So the distance, is 8 meters, right? There we are. Then that's just going to equal half mv squared. So there's going to be a bit of algebra here. And then minus a half m times 5 squared. So that's going to be a half times 5 squared. So it's going to be 12.5 m. And then minus 4.8 mg. And so there we are. That's the equation. Now we just simplify this if we can. So we're going to get minus 8/5 mg is going to equal half mv squared minus 12.5 m minus 4.8 mg. Okay. Right, again, don't be put off by the algebra. It's the exact same steps we've been doing so far, but now just a bit of algebra mixed in. Don't be put off. Now now remember, again, there's a lot of letters here, but we want to work out the final speed v. That's what we want to find v in all of this, nothing else. Now, actually, we can simplify this because m's are everywhere. So there's m here, m here, m here, m here, m here. So we can effectively divide everything by m to get rid of it. So that goes to minus 8/5 g is a half v squared minus 12.5 minus 4.8 g. Now let's bring in g's 9.8. Minus 8 over 5 of 9.8 is a half v squared minus 12.5 minus 4.8 lots of 9.8. Now if I just simplify this, I get half v squared. That's going to equal 43.86. I believe. Okay, so therefore v squared times by 2, 87.72. Therefore v, if I root that, I get 9.37 meters per second, and that is my value. 9.37. There we are. Cool.